In this next example of a hypothesis test for the mean, when the population standard deviation is known, we will be given the raw data rather than just the sample statistics. A car manufacturer introduces a new method of assembling a particular component. The old method had a mean assembly time of 42 minutes. The manufacturer would like the assembly time to be as short as possible, and so it's expected that the new method will have a lower mean. A simple random sample of assembly times, in minutes, was taken after the new method was implemented, and the results are given below. Assuming the population of assembly times is normally distributed, and the population standard deviation is 5.3 minutes, test the claim that the mean assembly time for the new method is less than the mean assembly time for the old method. Use a significance level of 0.01, and here are the raw data values in minutes. Okay, let's look back through the problem and see what we need to note. The old method had a mean of 42, and the claim is that the mean time for the new method is less than the old, so we can see our claim is going to be less than 42 minutes. And we'll write that up here in just a minute. We have a simple random sample, and we have a normally distributed population. We have a standard deviation for the population of 5.3. So let me note that. So sigma is 5.3 minutes. Our alpha is 0.01. Okay, and so now let's write our original claim. The claim is that the mean time is less than the old mean time. The mean for the new method is less than the old, which was 42 minutes. So the competing claim has to cover every other possible outcome that would be the mean greater than or equal to 42 minutes. So our null hypothesis is always that the mean is equal to, in this case, 42 minutes. And the alternate hypothesis here corresponds to the original claim. Note that the condition of equality is with the competing claim. Okay, so we will get a critical value. The calculator will provide our test statistic and our p-value. We will use that information to draw a decision diagram, and we will make a decision. Okay, let's look at our decision diagram. This time the alternate hypothesis is a less than sign. It's pointing to the left. This is a left-tailed test. And this area here is our alpha. And we were told to use an alpha of 0.01. So from that we can get our critical value using inverse norm function, area to the left, which is 0.01, distributions, inverse norm, 0.01, negative 2.326 rounded to 2 decimals would be negative 2.33. We were expecting a negative because we knew we had a left-tailed test. Okay. Now we're ready to enter the data in the calculator and do our z-test, stat, tests. The first one there is z-test. Okay, we have data this time. So, of course, I'm getting ahead of myself, aren't I? We need to enter that data into a list. So, we say stat, edit, and the first edit is highlighted, enter. And in my list, I need to enter the data that was given. So we had 27, 39, 28, 41, 47, 42, 35, 32, and 38. There were 9 values, so list 1, value 9, that was it. Now it's looking for the 10th value, but I don't have 10 values. Okay, now I'm ready to say stat, tests. We want the z-test, enter. So now that I have data, I'm going to highlight data, whoops, with my tab, enter. So now data is highlighted. My HO, the value with HO, is 42 minutes. The population standard deviation we were given was 5.3 minutes. The data is in list 1. If it wasn't, I could just tab down here and change it, but it was in my list 1, so I can leave that. Frequency is always left at 1. And we have a left-tailed test, so I'll tab to the left-tailed test, highlight that, and I'm ready to calculate. Okay, so we get a test statistic, z equals negative 3.081, rounded to 2, that'd be negative 3.08. And my p-value rounded to 4 is going to be 0.0010. Okay, so we said test statistic z equals negative 3.08. P-value is 0.0010. Okay, negative 3.08 will be out here somewhere. And so therefore the p-value, of course, is the area associated with the test statistic, so it's this little bit of area right here. So our decision is based on 2 questions. One, is the test statistic in the critical region? Yes. And is the p-value less than alpha? Recall that alpha 0.01, 0.001 is definitely less, and we can visually see that. Now we don't need both of these questions to be answered. One will give us the correct answer, either looking at the test statistic or the p-value, but since the calculator gives us both pieces of information, I like to check and be sure they agree. They should agree. Okay, so our decision here then is to reject the null hypothesis. Okay, now all we need to do is write our conclusion. Does the original claim contain the condition of equality? No, it does not. The condition of equality was with the competing claim. Did we reject? Yes, we did. So our conclusion is that the sample data support the claim, that the mean assembly time for the new method is less than the mean assembly time for the old method. And let's just point out again how we wrote that conclusion. Since the original claim does not correspond to the null hypothesis, rejecting the null hypothesis then gives us some support for the original claim. And that's what we've stated.